we're going to be talking about Green's theorem. So Green's theorem provides a relationship between the integral along a path and the double integral over the region contained by the path. And the relationship is as follows. So to get an intuition on how Green's theorem works, we will always think of being in the context of the vector. So let's draw a simple vector field like this. And all the vectors are pointing. Green's theorem says that if we walk along a path, if we walk along a path within this vector field, and we walk along the path in a way such that the region bounded by this path always remains to the left of the path, by convention. The path that we walk along is positively oriented if our domain remains to the left of our path. If we were to walk along the opposite path, or the opposite way, then this path integral will be negative. So let's draw our magnetic vector field, and let's call this vector field. Let's define it as negative y. And it looks like this. And let's say we want to find the total magnetic force experienced by the functions, or experienced by a particle that walks along the path of these two functions. So let's call this path C, and let's call the region in between it D, and let's define D to be the set of all points such that x is between 0 and 3, and y is between 3x squared and 3x. If this is our vector field, and we'll call this P, Q, we can directly apply this information to Green's theorem. It's equal to the double integral of D, and we just plug it into our Green's theorem over there, dq by dx. So if this is q, and we differentiate this by x, we get 1. And we subtract dp by dy, so this is p, we differentiate it, we get -1. We might just simply do the double integral of 1. So our x is bounded by 0 and 3, and our y is bounded by 3x squared and 3x. And we can use Maple to compute this integral. Another interesting application of Green's theorem applied to Kepler's second law of planetary motion. And the second law basically states the area swept by a planet in orbit along a time interval t change in theta, it remains constant if we travel along that same constant. So we can write this down mathematically by saying, if for a time interval theta, so it remains constant, which is our area swept, is equal to. So we can prove this relationship using Green's theorem. We want to compute the area swept by this interval theta. We can take the area by taking the double integral and taking the function to be 1. We have to pick functions p and q such that this relationship is true. If we take p to be -1/2, and we take q to be 1/2. If we differentiate p with respect to y, we end up with -1/2. And if we differentiate q with respect to x, we get 1/2. 1/2 minus 1/2 is equal to 1. We can now plug this into area is equal to the path integral along C of P plus q. An ellipse can be represented. So we can reparameterize this with respect to theta. So dx is equal to negative a sine theta dy is equal to b cosine. We can simplify this, factor out the 1/2 with y, so b sine theta. Dx, which is negative a sine theta, which is a cosine theta, multiplied by dy, and we want to integrate them. We can factor out a and b, there's no constants, sine squared theta, cosine squared theta, and we know that this is equal to area swept by an interval from 1 to theta 2. We have a relationship for the area. So we can simply find this integral from theta 1 to theta 2. d theta, and that's simply AB2, theta, and theta 1. So from this relationship, we can see that for any difference in theta, if this difference remains constant, we get the same area. So if we were to say that this was from 0 to pi over 3, we end up with an area of AB2 of pi over 3. And if we were to get the same pi over 3 interval, and we start from, let's say, pi over 2 to 5 pi over 6, see that this area is AB over 2 pi over 3, which is the same area as this.